until now, we've been talking about designing a deck from the perspective of its use, the client requirements and sort of laying it out. But now we've got to start looking at how it's actually going to get built, or the structure of the deck. So you need to get a piece of paper. Graph paper is usually easier to work with. And we're going to be drawing a number of elements and using the terminology for drawing. And I'm going to have a top view, how we see the deck above. In the upper left-hand corner, immediately below that, I'm going to have a side view, how we'd actually view the deck from the side. So I'm going to draw some basic elements here. We're going to draw a rectangular deck, a real simple type of deck design. This is going to be approximately 8 feet by 12 feet, and it doesn't have to be drawn to scale or anything like that. So that's my top overall view, and this is my side view. And what we're actually drawing is the outer edge of the deck, as well as the side or the joist heights. Joists or floor joists are what support the decking material, and then the floor joist sits on beams. So all along here, you're going to have basically floor joists laid out in this type of pattern, and it'll take me a couple seconds to draw, and that's why I'm drawing this as opposed to simply providing you with a sheet of paper, because I want you to sketch along with me. And your sketch doesn't have to be accurate, but what it does have to be is understood by yourself, and notes have to be taken on it so that you can actually refer to them when you start working on your own project. So these are the joists. Now obviously there is a joist in the end here as well, and there's one in the beginning or at the opposite end here as well. And there we go. You notice it doesn't have to be perfectly drawn or anything like that. It's just to give us an impression of what the object is. So this is my top view. What I would actually see is the framing from above. This is my side view. Now obviously this has to get supported. The weight has to transfer from the deck boards to the joist, and then from the joist to the beams. And that's what we're going to be drawing here right now, is the actual beams. Sorry, I erased that accidentally. Let me just draw that back in. So now we're going to draw the actual beams. And in order to do so and to make it a bit more visible, I'm going to just change colors. So this joist gets supported by a beam. And a beam is any sort of member that is either 3-ply, 4-ply, or 5-ply of 2 by 6, 8, 10, or 12. Those are the common sizes. And we'll have two beams that will support opposite ends of the joist. And then I'm going to show it in my top view where approximately they'd be sitting underneath the actual joist. Now you'll notice I'm not drawing them to the absolute end. And there's a reason why. So when we look at weight and weight distribution, the loading of the floor joist, the overhang portion of it actually pushes down on the beam in this direction and therefore pushes up on the floor joist. So it's far more efficient to move the beams inwards than at the outer end. Imagine, if you will, if these are at the outer end and you're standing in the middle, there's far more bend that's going to occur in the middle. If the beams are inwards, as I've shown here, and you stand in the middle, there's far less. So even though it's the same size framing member, because the supports are closer together, it has what we call deflection, far less deflection occurring in the center. And in fact, if we have handrails and people standing on the outer edges of the deck, the inner edge actually stiffens quite up. In fact, you'll notice things like truck flatbeds and things of that nature, they actually have an arc already designed in them, and the tires are inwards. They're not on the very edge, just for that same reason. So let's talk about loading here and some of the things that we need to understand when it comes to loads. So I'm going to draw some information on here. First of all, I'm going to put up some dimensions. So as we mentioned earlier, this is 12 feet on one side and this is 8 feet on the other. And we can all agree, I believe, that this deck itself, because of its shape, it's very symmetrical. This deck itself, if I drew a center line, and a center line is drawn with a long line, a dash, and a shorter line, and that simply represents that this line work is right through the middle. Then on opposite sides, we have 6 feet of deck supported on this beam, 6 feet of deck supported on that beam. And that's how we determine how the load is distributed. So on this beam there's 6 feet, on that beam there's 6 feet. So how do we come up to that number? Very simply, we take the overall number, 12, and divide it by 2. So all along here, it doesn't matter where we actually have the deck itself, or where we've placed different loads along here. The load distribution is equal, and that's what we consider when we're looking at the Ontario Building Code. So we have dead loads, which are loads that are part of the structure, so the floor framing, fixed planters, and then we have live loads, things like people walking across it, or movable objects, carts, furniture, things like that. But the overall building code considers all the weight of all those elements on all these items. That's why we can only use items that are designed for residential applications. We can't use a commercial barbecue on here because the weight is too heavy. So there's our calculation. And this 6 feet has a very specific term. It's called the supported length. The supported length is the amount of weight that is supported by the beam. And the supported length is part of the calculations when we look at charts and how it actually works. So imagine, if you will, we'll have a couple of columns underneath here supporting the beam. And again, notice I'm drawing the columns inward. And there is my column here. Actually, I'm going to undo that one because I could easily have drawn this with the rectangle tool. There we go. We have a column underneath here, and that column will be embedded into the ground, and depending on what's above it, sometimes it needs a footing, sometimes it doesn't. And this is how we do our calculations. We determine the supported length of the beam. Now, the maximum that we can move inwards on any length, or I should say overhang on any length, is 2 feet. So a 2-foot overhang is measured from the center of the weight that's being supported, so the center of the column, to the edge of the beam. It's also from the center of the beam to the edge of the joist. Those are our 2-foot maximums. And we always try to make those or maintain those throughout the project because that makes it very efficient. If I were to move this column right to the edge and right to the edge, I need a bigger beam to support the exact same load, the exact same weight. So it's very critical that we keep those things in mind when we're designing decks, or when we're building decks, or when we're framing out the deck plan. So how does this work with a larger deck that has multiple beams? Okay, let's take a look at that. I think you can all agree to this point the logic is pretty simple and straightforward. So let's take a look at an oversized deck, something that has a lot of distance to it in one direction. There we go. Let's do something like that. And in the framing or the side view, you'll see that we have joists. And we always show it as one long joist member, although they could overlap in the center. So my joist within this space would span the entire length. In actuality, depending on where the beam is, your joist may not be that long. You may have one that comes up to that size, and then another one that would come right beside it and overlap the beam. So I'm demonstrating how you'd build it, but I'm just showing you in terms of the drawing, and this will be how you draw it in CAD, not with the overlap. We allow the builders to determine where those overlaps are. They'll follow a certain technique that they need to in order to make sure that they're creating it properly, but we don't want to show them how to build or tell them what to build and how to build it. We want them to use their own techniques that meet code. So you can imagine, if you will, there are going to be 3 beams here. So we're going to draw one beam here, one in the middle, and notice I've got my overlap in the middle, and one at this end. This is a different scenario from what we saw before. Now, it may look the same, but there's a significant difference between this. So there we have our 3 beams. So let's come up with some numbers. What I'm going to do is switch to the pen tool here, and let's say the overall distance here is, let's go 30 feet. So what does that mean? I know I can have a 2-foot overhang here. I know I can have a 2-foot overhang here. There's no overhang in the middle. The weight that's being distributed between these 2 columns, or sorry, between these 2 beams, is again evenly through the center between those 2 items. So that is the basic physics behind something like this, is that we have a center line here, we have a center line here, and that's the weight distribution. So what do we know? This is 30 feet. Let's say these are all evenly spaced, which simply means this overhang is 2 feet, this overhang is 2 feet. The distance between edge to edge is 15, but we subtract 2, so therefore from here to here is 13 feet. So that is from the center line of this to the center line of this, and then we have the same here, 13 feet to that center line here. So let's draw a horizontal line and put in these little oblique angled lines to simply demonstrate the dimensional values. 13 feet and 2 is 15, 13 feet and 2 is 15, 15 and 15 is 30. So how much is actually being supported on each beam? So what's half of 13? Well, that's 6.5 feet. So up here I'm going to put down 6.5, and that's in feet. This is 6.5, and that's in feet, 6.5, and 6.5. But we also have this 2-foot overhang. So let's take a look at how this weight is distributed. Sorry, my screen jumped there for a second. I've just returned it to its proper view. So let's see how this weight is actually distributed throughout this. So again, using the same principles of what we had here, I'm just going to draw some arrows just so that you can see. And I'm going to change the color just because I want to make it very obvious to you how this is actually occurring. We can agree that half of this line, half of this length is distributed onto that beam. Okay, so let me just make sure that I've got the right dimensions for that. So that is 6.5 feet and 2 feet, which in this particular case is 8.5 feet. And when I say 0.5 feet, I mean half foot. So it's 8 foot 6 inches. Now, if I take a look at this segment, it's the same sort of thing where there's my center line. And then I have some arrows that I'm going to be drawing here to represent this second segment. And you can agree that this center beam is supporting that weight, and this weight. So that's not the same. Even though it looks like it's symmetrical at the top, it's not the same weight distribution. So what is the actual weight of that item there? Well, let's take a look at it. We have 6.5 feet, 6.5 feet, which means it's 13 feet. And then the right side is the same as the left side. So once again, it's 8.5 feet. And the weight distribution of the actual load that's coming down is the same as on the left side, where it's that weight along the center line to the outer edge. Notice the 2-foot overhang is being supported by that beam. Half this weight is being supported by that beam. And then same on the opposite side. So when we look at this, the outer two beams are actually far less load-bearing than the center one. In fact, these dimensions here, which again refer to the supported length, is very critical in determining the size of the beam, regardless of the columns. Typically, the columns will place in exactly the same location in this sort of area, just so that we can understand it. And I'll show them here. Obviously, we have one that's approximately 2 feet in, 2 feet in, and we lay it out more or less like a grid, so it's very easy to place on the ground. So those are all 2 foot in, 2 foot in. So the actual supports of these, sorry, I used the wrong shape here. The actual supports of these will be located here underneath the beams. And again, it's a very good thing to sketch this out, because when you start doing calculations, these are the sketches you're going to be providing to me to identify what the different elements are. Supported length in this particular case, to determine how much weight is over the beam. Now we can all agree, if we take a look at this, if this is an 8-foot width, there's a 2-foot overhang here, there's a 2-foot overhang here. This is a very short segment. So we basically only have 4 feet of beam that's being supported by these two columns, and that's consistent throughout this whole project. So hold on to this. We'll be making notes on this one a bit later. And now I'd like to take a look at the Ontario Building Code. Okay, for this segment, I want you to pull up 3 PDF files that are included in the Lesson 2 folder. They're all about floor framing. So you have, they're all referred to as Chapter 3. There's ones on beam calculations, on floor calculations, as well as a chapter on basic information. So let's go through this to try to understand what it is that we're looking at. And I'm going to highlight some things. Now, I do suggest, not this sheet, but the other two, that you do print out, because you're going to have to highlight and add some information to it just to make sure that you understand it. So let's take a look at this. This talks about load sharing and how we actually showed, or we share load. The joist members in here that travel in this direction, so they run the length of the structure and they're supported on beams. Now we can actually make these more rigid and stronger in a sense by adding different configurations. Strapping is the basic way that a deck is put together. So the decking itself adds that strapping quality to it, as well as the beams. So we really don't need to do anything to strap the joists in this particular case. Cross bridging adds a lot of rigidity and strength to the joist. So if our numbers run short, we may add cross bridging, and it'll actually provide extra strength. Now, the other option in here is called blocking, and that's what this talks about here, solid blocking between joists. So this member here will actually add significant strength, and blocking, which is this piece of wood, which is the same height as the joist. So if these are 2x6 joists, use 2x6 blocking, can also replace cross bridging. Cross bridging in some cases may be more expensive, but in other cases it's cheaper. It all depends on the labor. There's far less labor involved. It's easier to put in blocking than strapping, and that's what the considerations are. So remember, cross bridging, blocking, and strapping are 3 different ways of framing the floor joists to make them stronger. So now let's take a look at the joist framing here. And this is right out of the Ontario Building Code. It's the same code that we use for floor framing. So it's not something that is different outside or inside. We use the same sort of concepts. And here's our terminology where we use strapping, which is consistent with any project that you work on, bridging, or bridging and strapping. And it's information that you need to know as we start working through this project. What else do we need to know? The spacing of material. You'll notice in here, let me just scroll that out, I drew the floor joists along here. The spacing is the distance between these floor joist members. So that's something that we have to be aware of and basically look at the code to determine what the spacing actually will be. So we try to use 16-inch centers in all cases. That's the first segment that we go to because it's the most efficient. 12 inches on centers is more rigid, but it's also more costly. For every 4 feet of flooring, we actually need an extra joist. So for 4 feet at 16 inches on center, we need 1 fewer joist member than at 12 inches on center. So it saves us money. So that's why we look at the 12-inch center columns first. So what do these numbers mean? 2x4s we don't use. 2x6s are very small applications. Typically we'll use 2x8s, 2x10s, and 2x12s. So like I said, we could use a 2x6, but it's typically for a very small application. What we don't ever use is this column here. So you may say, well, why aren't we using that one? The spacing of 24-inch centers, depending on the deck boards you buy, it doesn't identify what size deck board, could actually break under heavy loads or if you put them in diagonally. So let's not use any 24-inch centers when we're doing our calculations. So what do these numbers actually mean? The important number are these in the middle. So for instance, at 16 inches on center, I'm just going to draw an underline here. At 16 inches on center, a 2x8 can span 11 feet. That's how we read this table. That's only with strapping. Now, If we still want to use a 2x8 but want to get more length out of it, we go to bridging. And that's 11 feet, 8 inches. That's how we read the chart. So let's just move this over here. I'm just going to minimize this page and slide it over here. There we go. I moved it a bit too far. I'm sorry. Just be patient with me. There we go. So I'm going to take a look at this table that we've been working on and see there is our span. We talked earlier about supported length, and now we're going to talk about span in the drawing. The span is from the beam to the beam. So what is our span length? Well, when we take a look at here, down here, we use the numbers of 6. That's the actual span of the joist, or the length of the joist, but it's not the span. The span is the distance in between. So let's take a look at this. How can we work with those types of numbers? All right, I'm going to switch to the pen here. I have 2 feet, I have 2 feet overhang. Let me switch to red. I have a 2-foot overhang here. And it doesn't want to switch to red. Okay, hold on. Let's see if I can do it this way. I'm not going to fight it. So anyways, sorry about that. Let's see if I switch color number 2. I'm being a bit stubborn. So I have a 2-foot overhang here. There we go. I have a 2-foot overhang here. The overall distance is 12 feet. 12 feet minus 4 is 8 feet. So the actual span, the distance from the center of this to the center of that, is 8 feet. That's the number we have to consider that the joist is needs to support. Now, even though the joist is 12 feet long, we're only calculating it by 8 feet. Remember I mentioned earlier the importance of this 2-foot overhang. Because if I didn't include this 2-foot overhang, I'd be calculating it on a 12-foot measurement, which is significantly different. In fact, let's take a look at the table in the chart to determine what the difference in numbers actually are. Okay, so if I looked at the 8-foot difference, there's my 8-foot value right in here. Let me just change this color so you can take a look at it. I'm going to really make it bright. This would actually fit, a 2x6 would fit with strapping only over that 8-foot distance. Whereas the 12-foot distance is this one here. I'd have to go to 2x10s. What a significant difference it is to go from a 2x6 to a 2x10 just because of that additional 4 feet. That's why when we design the structure, we have to be very efficient in how we're laying out the beams. It's the same distance when we're looking at the overall picture here. This is still 12 feet long. But if I move the beams to the end, that joist has to be a 2x10. By moving in 2 feet in both directions, it's now a 2x6. And that is a significant cost savings, plus the deflection, how it bounces, is going to be significantly different. So this number down here represents the joist span. So let's start making some notes here to say what these different things are. So this is the joist span. And in this particular case, what are the joist spans here? Well, let's take a look at up here. We did some numbers already that helped us with it. In fact, when we did this, we didn't realize that this number that we came up with, the 13 feet, is actually the joist span. So the joist span itself, because we moved it in, again, significantly different between 13 feet and 15 feet. Let's see how that affects our Ontario Building Code. So I'm going to slide back to that. 13 feet versus 15 feet. So on this page here, I'm simply going to undo those two numbers. And let's take a look at 13 feet, which would be this one, versus 15 feet. Well, this doesn't actually go to 15. I would now have to include bridging in order to make that 15-foot distance and change from a 2x10 to a 2x12. That 2-foot overhang is absolutely critical in anything that we're doing with our measurements. But you can see how we actually calculate floor joist spacing. All right. So considerations. Look at this table. you'll notice that we really can't get past, in fact, the Ontario Building Code says we can't use this number. We can't go to 16 feet. We can't go past that number. We have to stay underneath it. Why they have that in the chart, really we should cross that out. And I'm going to do that right now. So remember, this number is not available to us. Where else do I have that? Here. And that's it. Because it's not permitted by the Ontario Building Code. We can only go as far as up to 16 feet, but we never want to max that out because that really pushes the values that we're working with. And if there's a slight variation on site, they can't do it. They can't put the framing members in. So there's the information we need to know. We stick with, or we go first to the 16-inch centers, and then we adjust from strapping to bridging and strapping. If we can't meet the criteria there, then we switch to a 12-inch center on our floor framing. And that's how we determine this. So in this particular case, you can see the span here is 12 feet. The span here is 13 feet. The overhang is 2 feet. Those are all critical measurements. So how does the supported length work? We're going to be looking at that next. So in calculating beams, it's a bit more complicated, but it just needs a bit more focus. However, before I move on, I just want to mention that I'm going to be going through this entire process again to determine my own project. So I'm going to go step by step with my project before you apply it to yours. So some of this more complex things we're going to be reviewing several times just so that you understand. I've switched now to the maximum span built up floor beam chart so that we can understand what it is that we're going to be doing. So we can calculate all our beams here. So again, this is a bit overwhelming until we break it down, but it's really not that difficult. When we're determining our beams, we only look at number 1 or number 2. We don't look at structural select. Structural select is way too expensive, and quite frankly, you'd have to order it in. So basically, we're not going to look at that. And then up above, we're looking at the different framing members. You'll notice there's 2x8s here. There's 1, 2, 3, and there's 2x10s here. There's 1, 2, 3, and then 2x12s as well. And then it has above it a certain number configuration. So here it shows there's 3, there's 4, and there's 5. Ignore the other numbers because that refers to metric sizes. We don't use metric unless we're in Quebec or we're doing a government program. So let's ignore that altogether. So right now we're down to this bottom portion of the chart, okay? And we're only looking at the numbers that are above. So let's try to make a sense of what this means. First of all, I want to explain what this 3, 4, and 5 refers to. So I'm going to go back to this drawing here, and I'm going to switch to the rectangle tool. So we're looking at these beams here, and essentially when you're looking at a beam, it's made up of different pieces of wood, and those beams can either be in 3-ply or they can be in 4-ply. Okay, I just undid something. I'm not too sure what. Sorry about that. I'm going to draw up here, see if that's a problem. No, there we go. So it can be in 4-ply or it can be in 5-ply. That's a 4-ply. Running into a bit of a problem here. There we go. I've got my hand on the drawing tablet. And let's see if I can draw a 5-ply. So that means the number of layers that this beam actually is. And those layers are basically glued and then they're screwed together. And there's some very strict requirements on how that's done. So this up in here, I'm just going to switch pens so you can see the notations I'm going to make. This is a 5-ply in here. So that would be 5 2x8s, 2x10s, 2x12s. This would be a 3-ply. And down here would be, oh, I made a mistake. Apologize for that. This is a 4-ply. This is a 3-ply, and this is a 5-ply. That makes it a bit simpler. So that's the number of pieces of wood that are screwed and glued together to make up one of these beams. So when we're doing our number calculation, scrunching, we're looking at the center of the beam. And the reason we look at the center of the beam is because the center line of the beam doesn't change. It's in the middle of the beam. We don't know when we're doing the original calculations what size beam we're going to be using. So all of our measurements are based on the center of the beam, and that's important. So again, 4-ply, 3-ply, 5-ply. Let's take a look at the Ontario Building Code to see how it's laid out for us to understand how we can actually design a beam. So, oops, that's the wrong one. That's the floor table. There we go. So what about these other numbers that are here? The most critical number that we're working with in the beginning is our supported length. So the supported length, that color, actually it's a bit dark. I'm just going to go with a lighter color so it doesn't interfere with what we see in case you want to print any of this stuff out. So there's my supported length. That number is this one right here, 7'10", 9'10", 11'10". That number is critical to determine which row we look down. And then that row, it determines the actual columns that spacings so that we can actually look at what beams we need. Let's try to run through the example that we've been working with. Okay. So here our supported length in example number 1 is 6 feet. So that is the length that goes that the beam supports from one end to the other. So this is 6 feet because it has a 2-foot overhang. This one in the second example we had 6'5" plus 2, so that's 8'5". The middle supported 13 feet, and then the opposite end supported 8.5. So these are our supported lengths. You can see that the center beam supports much more than the outer edges. So let's take a look at this one. 8 foot 6 inches. Okay. So if I go back to my table that I have here on the actual beam support for that example, and again, we're looking at that example only. So I'm going to show all of that in green. It was, I already forgot it. Sorry about that. Let me just go back to it real quick here and look at the number. So the first one was 8 foot 5 inches as a supported length. Okay. So this is where it's really helpful that you have everything printed out and in front of you because it's so much simpler. 8 foot 6 inches. So I can't use this one. I can't use the 7'10". I have to go to this one. And that one there, I'm going to be using 9'10", even though it's far greater. Now, the numbers here indicate the column spacing. How far apart are the columns for this particular example? Let's go back to the drawing. And in the drawing, you'll notice that the columns are really close together. They're only 4 feet. Now, what that simply means is that we could have the columns far further apart for any of our calculations. But in this case, we have 4 feet. Again, the overhang is 2 feet on either side on an 8-foot deck. So we've got very little column spacing. 4 feet is really minute. So if I go back to the actual example, here, 4 feet, all of these meet 4 feet. So I can go with 3 foot or 3-ply 2x8s. It'll actually handle 9 feet 4 inches. And that helps me look at how big my column spacings should be. So if you understand that concept, these numbers in the brackets are how far apart the columns can be. So let's take a look at this. We can range, and I'm going to use a different color so you can really see the range that we can work with here. Let me use that bright blue again. We can go with, depending on the supported length, column widths anywhere from 10 feet all the way up to, we can go 12 feet, 13, 8, 15, 9. So you can get a pretty good spacing or distance between columns. What I recommend is simply this. Let's get back to this particular diagram here. And I'm going to go back to the pencil tool. For your columns, have your spacing somewhere between 12 feet and 14 feet. So that means from that distance to that distance. That's a good column spacing right there. 12 feet to 14 feet. You know your beams themselves. Let's take a look at this one here. This has a supported length of 13 feet. If I go back to that table that we were working on a bit earlier, supported length of 13 feet. So that this particular one, I would have to use this number. And again, you can see right away that 8-foot piece would work, no problem. Let me just change that color so I'm not confusing anybody here. I'm going to go back to this light green. So 13-foot 9 is greater than the 13-foot requirement, and definitely I could use 3 2x8s. So what is this telling me? With that supported length, I could use 3 2x8s right up to 8 feet apart. I could use 5 2x8s right up to 10 feet apart. So let's take a look at another problem and work it through beginning to end. Okay. So all of these different elements play an important role. Try to stick with this number for my column spacing. Try to stick to, for your joist itself, the actual supported length. You can get away with this, 13, 14, 15 feet, but the distance between those beams, I would stick again somewhere between, let's say, 13 feet to 15 feet. And this may make it very easy for you to be very consistent with your deck design in how you lay out the beams. So let's try a working example from start to end.